So the next presentation from Professor Tang Luping.
Hello.
Yeah,
So
Professor Tang received his PhD in 1996 at Chalmers University of Technology, Gothenburg, Sweden. Since he has worked at the SP Technical Research Institute of Sweden for 12 years and rejoined Chalmers since 2008 as a professor and leader of research group for building material. His main research interest is new type of cementitious material and durability of concrete, especially chloride transport mechanism and chloride induced corrosion of steel in concrete. In the past year, he has been involved in several research projects dealing with the greener cementitious material, including nanotechnology and chemical activation. So please, Professor Tang, please start your presentation.
Thank you, Dr. Bao. Yeah, I think now I need to share my. Okay, I'm going to talk about the background and also laboratory experiments which we have done, and also preliminary results. Finally, give some concluding remarks. As you know that nowadays the whole world needs to consider this sustainable development. So we normally call it 3R, reduce, recycle, and reuse. So here we always consider how to do it. For instance, recycled concrete recycling, this is one of the important things. And in Sweden, we have also started this recycling more than 10 years ago. But as you know that if we want to have a very good recycled concrete aggregates, we have to crush it very hardly, very strongly. But then afterwards, we crush so many fines. So you can see that we have a statistic in Sweden that the particle size below 4 millimeter, that is almost 30 to 50% left. And below 2 millimeter, that is 20 to 40% left. So all of this fine particle size, in fact, particles, that is very difficult to be used in concrete. Yesterday, I really just contact concrete manufacturer that they said that they cannot allow to use these fine particles in the concrete production because of the poor properties for workability. So this is on concrete sites. In fact, we want to focus more about how to use the fine, because that is almost 30 to 50% quantity, which is dramatically large, in fact. So on the another side, this is municipal solids waste. We know that now we are using this incineration technique to handle this municipal solids waste. So this is called MSWI. The ashes from there, you can see that is also almost about 20% bottom ashes per ton. Per ton, I think that is per ton. Let me see. Yeah, per ton of incinerated waste. So this 20%, the question is, this 20% will just accumulate year after year. So how long time we can use it? Because now we have to use it for landfilling. But how long time we can? So this is also a question: how to treat, how to turn or use these ashes as a useful value added material. So this is, I think, every country is considering this question. Fortunately, recently the alkaline activation technique gets a very good development. I think Dr. Jin also our previous presentation exactly talk about this mechanism. I think that is very good thing. We did some work about this physical properties. The property here is shrinkage. Shrinkage is a big problem with this alkaline activated material. So you can see that when we add the alkaline sodium oxides, it will introduce some shrinkage about let's say about 20%. If we introduce silica from the water glass, it will increase even more shrinkage. So, but anyway, if we consider to add some gypsum, then we can compensate some shrinkage, because gypsum will form iron jet, which is expanding. So especially for the initial parts, so it can compensate more when concrete strength is low. So in this way, we can eliminate the cracks to some extent, but still it is still high shrinkage compared with ordinary Portland cement. So recently we have a publication for you. If you are interested, you can look at the article in Construction and Building Materials. I think we just published a few months. Then from our laboratory, we tested one Swedish recycled aggregate from an old bridge, road bridge. Then we, as I mentioned, our focus is on the fine parts, 0.024 millimeter. The density, as you know, because it contains a lot of mortar, so the density of recycled aggregate is relatively low compared with ordinary natural sands. The water absorption is also relatively high, 9%. So this is very high. So this is why we cannot use it directly into the concrete. Then we measured the mortar contents by different portion of size. It is very clear that the fine particle contains more mortar. So this is clear. So the large particle contains less mortar. So that is why large particles can be used easily, but not for the fine particles. In China, I believe they take away this part 0.125 millimeter. So means 125 micrometers parts they take away. They try to use these parts from larger than 125 micrometer. Even in this case, they found that only 20% replacements for natural sands can be used. Otherwise, it will decrease the strength. Water adsorption, here it is adsorption. We just put the sands into the chamber to adsorb the water molecular. So you can see that also the small particles will adsorb more water. This is also an indication of more mortar contents. Then from our previous research, which I presented last year at our first workshop, then we got a very clear picture that in fact, if we want to add 2.5 more water into the concrete, we get the relatively good workability. But we get the relatively low strength. That is almost the effect of water cement ratio. If we add the extra water or extra alkali solution, so it is almost the same. So we cannot directly use this technique by adding water into the fine aggregates, which will decrease our strength clearly. But if we use alkali activation, alkali activated slag with 80% of slag, 20% of OPC, ordinary potassium cements, then we can see that we can get almost the similar strength as when we use natural sands. So this means that in fact, if we use alkali activation technique, which can really improve both the workability and strength by using this recycled fine aggregates. But unfortunately, as I mentioned, so far the shrinkage is still large compared with the ordinary potassium cement. So now this year we also got two type of Swedish bottom ashes from two municipal solids waste inclination plants. So here it is the particle size distribution. But this particle size distribution, we do not use it because with this direct particle size, if we use it, we will get a big problem from the gas release because this particle size contains active mineral, which will expand afterwards. So instead, we ground all of these bottom ashes down to 250 micrometer particle size. So this is what we did. After grounding, then we can analyze the mineral composition. So here it is mineral composition. You can see that the bottom ashes contains calcium and silica. This is main parts, and also alumina. So this this alumina, the question is, this alumina is in fact it is not in the oxidized condition. In fact, it is not alumina oxides, but in most cases it is direct metallic alumina. So this will be a trouble when we use this alkali, when we introduce it into the alkali environment, because this alumina will release the gas under the alkali environment. But on the other hand, this harmful element also in the bottom ashes is also relatively high. But this is, I think, in the future's question, how to fix, how to solidate these harmful elements. Or this is a policy I cannot answer so far. Anyway, from our research point of view, we have to demonstrate the possibility. Then afterwards, the regulation work can continue. Otherwise, if we follow the current regulation, it is not allowed to use this bottom ashes into the concrete. So we also tried a very simple solution test to test the hydraulic activity of the bottom ashes. That is just simple with 1 molar sodium hydroxide under the high temperature curing for 7 days. Then afterwards we can determine hydroxide hydrates and hydroxide contents under the different temperature. Here we focus on the hydrates products between 105 degree to 350 degree. Then, so this way we can see that finer particle size contains more hydrates. But of course, here the question is that the raw and the alkali treated ashes contains almost the similar hydrates. So we believe that because this bottom ashes has already poured into the water for cooling and storage some 1 or 2 months. So during this period, in fact, the oxide mineral already hydrated. So afterwards, in fact, it already lose this further hydration property. So, but anyway, it contains some hydrates inside the particle, inside these ashes. So we try to use these hydrates to do the green sands. So we consider in such a way. In the rotation, you see here, we have this sand, fine recycled aggregate sands and bottom ashes, and with the alkali activator, which is in fact water glass based. Then under the rotation, we can release the gas. You can see this is before the gas release. This is after. So means that the alkali has already reacted with the alumina in the ashes to release the gas. At the same time, to form the new hydrate products, which will bind the recycled aggregates to form a better shape. So afterwards, we use also carbon dioxide to cure this green sands. So you can see we just use very simple homemade this carbon dioxide water instruments, very simple, to fill the bank, and then afterwards cure it. This is under the carbon dioxide environment. So afterwards, we got this sand distribution. So you can see that this is original sand recycled particles. Here we sieve away the particle size larger than 2 millimeter, and then we only consider more about the fine sands less than 2 millimeter. So you can see that after treatment, the particle size become coarser. The particle size become coarser. I think also become round, spheric, because of the rotation. We know that with the rotation, everything will become a spheric balls. Then if we use this Funk-Dinger model, we can, this is continuous particle size model. So you can see that our green sands follows this curve better, but still we can see that it is coarser than this Funk-Dinger model. So in our use, we still need some more recycled fine aggregates. So this is what we did. So we have some, you see, this is standard mortar. 1 cement, 3 sands, and 0.5 water band ratio. We found that all of this, and in our sands we have this about 30%. In this case, we have 30% natural sands in 0 to 1 millimeter, and 70% green sands, because as I mentioned, green sand is too coarse. It's coarser than the curve, so we have to add some fine particles in order to get to make this closer to the ideal curve. So here we have 30% natural sands, and then this is our first test. So you can see that the results, I just got the results yesterday, in fact, with the help of our Thomas Concrete's group because our compressive machine damaged yesterday, so I couldn't measure this 28 days results. So I have to go to another place to test it. So you can see that this is reference with natural sands. So this is with our 70% green sands. So you can see that in the beginning, this 2 days data, it is lower. 7 days, it is become closer. 28 days, that is completely similar. The reason is that our green sands, that is still under the hydration. So that means in the early age, the sand's strength is low. So with the time, curing time, because after casting this sand into the mortar, this sand is still under the hydration. So so the late age, the hydration will go up. So I think this is very positive results, which gave us promising future to how to use these fine aggregates. And then we also tested completely use this because in my previous test, we found that the workability is even too much, too fine. So instead, the natural sands. So this time, I used completely the recycled aggregates between 30% fine recycled aggregates and 70% green sands with this three. With this three mixture, 4 to 6. Then so far I have only 7 days data. So from the 7 day data, you can see that with especially with this one, I reduced a little bit water band ratio because we found the workability is too high, too flowable. So we increase it. It won't damage the workability, but then it is quite easy to cast. And in this case, we keep the same cement contents. So then we get almost similar results from this mix. This mix 4. So this is 7 days data. I believe that 28 days it will become even better. So this means that we can 100% replace the natural sands. So I think this is also good news. So I think this is also the time I have to finish it. My concluding remarks is from our preliminary experimental results, we can see that if we mix recycled aggregates less than 4 millimeter with 2.5 to 3% alkali activator, which can effectively keep the strength of alkali activated slag mortar at the same level as using natural sands. But this is not for the ordinary Portland cement binder. So this is, in fact, this is the conclusion from our previous study. From the current study, we found that pre-treating the recycled aggregates less than 2 millimeter with ground municipal solids waste ignition bottom ashes by means of alkali activation technique can effectively overcome the problem of fine recycled aggregates in workability of concrete, and at the same time replace the natural sands by 70 to 100% without markedly impairing compressive strength. So this is my conclusion. Okay, thank you for your attention. So I don't know if we have time, we can have a discuss. Otherwise we can continue. I return my presentation to our chair, Dr. Bao.
Thank you very much, Professor Tan. The presentation was very interesting and very clear, comprehensive. Thank you. Because we have 10 minutes late, so maybe we